All right, welcome everybody to today's seminar series in Physics Meets ML. We are very happy to have Yi-Zhuang or Everett Yu from UCSD. And so Yi-Zhuang is graduated from Tsinghua University and did a postdoc in Santa Barbara and Harvard, and before he moved to UCSD, where he is now. He is an expert in theoretical condensed matter physics and has done a lot of very interesting work in also entanglement and holography. He is one of the early persons who have really been pushing machine learning applications in these regions and has produced a lot of interesting work over the many years now. So we're very happy to have him here, and I'm looking forward to learn about machine learning applications to statistical gravity and entanglement entropy. Please go ahead.
Yeah, thanks a lot for Fabian, and thanks a lot for the invitation. And it's great to be here and talk to many old friends. So today I'm going to talk about a recent work that I have been doing. Actually has already been published on PRR with my student Jonathan Lam, using machine learning, try to uncover the statistical gravity model in the holographic bulk from the entanglement entropy data on the holographic boundary. Okay, so the problem we are going to study or to tackle is the so-called holographic reconstruction problem. And the goal basically is to reconstruct the holographic bulk geometry or even gravity model from a holographic boundary data such as quantum entanglement. And the idea is based on the idea of holographic duality, which is an idea developed in the string theory and quantum gravity research. So the holographic duality claims that there is a duality between the d-dimensional quantum field theory on the so-called boundary with the d+1 dimensional gravity theory in the bulk. And this basically, there's has been a lot of work since the proposal of this duality, and it also provides a very profound relation to connect emergent space-time with quantum entanglement. So one manifest connection between geometry or gravity theory with quantum theory or quantum entanglement is the Rita Kanaki formula. This formula relates the quantity of quantum entanglement, which describes the amount of entropy in a quantum system if you only look at its subsystem. Say subsystem is labeled by A, and if you ignore A bar, then the entropy associated with the subsystem is actually called the entanglement entropy. That's measures the amount of quantum entanglement of this region with the remaining A bar region. So it is relating this quantum entanglement to a geometric quantity, and the geometric quantity is basically the area of minimum surface in the holographic bulk that this minimum surface basically covers this region A. So from the intuition actually originated from ADS-CFT that in a 1+1 dimensional conformal field theory, the entanglement entropy in a region A, suppose it's a single region, then it's basically proportional to log of this the size of this region. But in the ADS, using ADS-CFT correspondence in the classical gravity limit for holographic CFT, it is understood that there is an ADS bulk dual, and in the anti-de Sitter space, we only in terms of since we are talking about entanglement entropy, which is an equal time idea, then it also corresponds to a bulk. We only need to take care about the equal time bulk, which is basically a hyperbolic space. And then in this hyperbolic space, the minimum surface is actually correspond to the geodesic through this hyperbolic space. But then one can already show that this geodesic length is basically proportional to log of the size of this boundary region A. If this geodesic is going to start from one entanglement cut and end up with the other entanglement cuts. So this kind of log A, basically dependence, is a very strong hint that entanglement entropy can really be interpreted as a geometric quantity in a one higher dimensional system. So this Rita Kanaki formula basically provides a geometric interpretation to quantum entanglement. So given this kind of connection, then there's a lot of work trying to understand the inverse problem. So the inverse problem is basically the bulk reconstruction problem, is to say that, okay, entanglement has this geometric interpretation in the holographic bulk, but then maybe we can start from this boundary data about entanglement and try to reconstruct the bulk geometry or even the bulk gravity theory, hopefully. So, so there has been many approach that has been discussed very recently. And then some approach based on geometric quantities, like if I know all the data of geodesic lengths measured from the boundary, or if I know all the extremal surface area also measured from the boundary, or if I know the entanglement data, that means the entanglement entropy in different regions of the quantum systems, can I reconstruct the bulk geometry? So that's basically the question. And then many of the previous work basically focus on the single region entanglement, which means this entanglement subsystem is a singly connected, just a single region. And then using those data, one can already basically extract a classical bulk geometry, basically fit a classical bulk geometry. But this work, we are going to also study multi-region entanglement, which means this subsystem is not only a single region, but a different region jointly different region. It's not simply connected. So so these multi-region entanglement turns out it will provide us more information about the bulk, including the fluctuating bulk geometry and maybe a statistical gravity model behind that. So that's basically the goal. And then talking about multi-region entanglement, the most important, or maybe not most important, basically the simplest feature of a multi-region entanglement, the simplest example is the mutual information. So the mutual information is defined between two regions in the quantum system. So suppose you have a quantum system on the boundary, and then there's a subsystem A and the subsystem B. Mutual information describe the amount of information that you can know about A by observing B, basically. So it is given by the entanglement entropy of subsystem A plus entropy of B minus entropy of A and B jointly. So in terms of the bulk description, because the entropy is interpreted as the minimum surface area or the geodesic distance in the 1+1D case, so it basically can be written as this one. So if we consider a classical bulk, and then if we have two regions, A and B, far separated from each other, so you just imagine A and B are small, and they are far separated from each other, then basically this joint geodesic, which means the geodesic that should simultaneously include or covers A and B region, so they will break up into two separate geodesics. So that's why the joint geodesic is basically the separate geodesic add together. So in this way, there is no this difference between these quantities. So the mutual information is 0 for far separated region A and B. So that is actually true for holographic CFTs, where the bulk gravity theory is just classical, and then that's actually the expected behavior, that there's no mutual information between distant regions. But this is not generally the case for many other quantum systems, such as free fermion CFT. For free fermion CFT, for example, we know that the mutual information between far separated region A and B does not vanish immediately, but it vanishes with a power law behavior. It vanishes in a power law, basically -2 power law with respect to the distance between the region A and B. So how to capture this non-vanishing mutual information in many in more general conformal field theories? So there has been two ideas. One idea is to introduce some bulk quantum field theory to mediate the mutual information through the bulk. So this idea has been explored by many different groups. And there's another idea, it's not using a matter field to mediate the mutual information, but using the gravitational fluctuation, gravitons, to mediate the mutual information, which is which is this work, which is what we want to explore more. So the idea is, since the idea of basically the observation is that the reason that this AB mutual information vanishes is because there's no interaction between these two geodesic. But the way that the two geodesic can interact with each other is if there is a gravity field, and if there's a fluctuating gravity field that can mediate the gravitational interaction between the geodesic. These geodesic are like trajectory of test particles sending into the bulk. So if they can gravitate each other, then it is possible to create some amount of mutual information, because the total geodesic in the presence of both particles will be different from the sum of each of the geodesic in the presence of gravitational interaction. So that means this the mutual information, these kind of data, this multi-region entanglement data that is already presented in a quantum field theory, actually can give us some hints about what kind of gravitational fluctuation there should be in the bulk. So basically that's the goal of our study, and we try to look at these multi-region entanglement and try to extract what it tells us about the gravitational fluctuations. So we will use statistical machine learning to extract those gravitational models from entanglement. So that is the main thing. Okay, so in order to establish our basically calculation or model on a solid foundation, we basically use basically a framework that we use. It's called random tensor network holography. It is one very interesting idea starting from the tensor network representation of a quantum many-body state, try to understand why there is a duality between a quantum many-body system and the gravity and the holographic bulk. So the idea of tensor network is basically try to represent many-body states. So suppose I have 10 particles or 10 qubits, let's say. So and then I want to describe its wave function. I can describe the state vector or wave function of this 10 particle by a rank 10 tensor, basically. Each tensor element corresponds to a wave amplitude. And then the tensor indices basically corresponds to the labels of the degrees of freedom on each particle. If I have 10 particles, then I have a basically 10 leg tensor. It's like that. So that's the general idea. But the tensor network is saying that, okay, you don't really need to use a huge big tensor to describe all of it all in one go. You can basically break up a large tensor into the contraction of smaller tensors, such that these red nodes is basically a smaller tensor. They connect to each other, and every line that connects two tensors means that these two tensor degrees of freedom are contracting with each other. So the amount of degrees of freedom that is contracting with each other along this bond is called the bond dimension. It's basically the Hilbert space dimension locally on the bond. And then every tensor, you can make it simple such that it provides some more intuitive or simpler description of the whole wave function. So every tensor network basically represents a quantum many-body state. And the network geometry, which is how the tensors are connected, actually is related to the holographic bulk geometry. So the degrees of freedom, quantum degrees of freedom, are these blue dots that is living on the holographic boundary. And then these red degrees of freedom, the tensors, basically lives in the holographic bulk. So in the random tensor network, this random, what does it mean by random? Means that all these red tensors, they are considered as, they are treated as random tensors. So to be the reason that they are random because we don't want to just describe one particular state, but we want to describe an ensemble of quantum states which has similar entanglement properties. So we don't really care what this wave vector, which tensor element it should be precisely, but we care about the general behavior, the overall behavior of entanglement, and we care about the geometry in the bulk. So that's why we just ignore these details of the tensor elements, so we treat them as random tensors. So the conventional random tensor network is basically a network of tensor contractions with random tensors with fixed bound dimension. You need to assign a fixed bound dimension to each of the leg. And this kind of framework, on one side, it represents the quantum antibody state. But on the other side, it also has a geometry interpretation. So it connects entanglement with geometry. And it is found that this model can nicely reproduce the Rita Kanaki formula in the large bound dimension limit. So, sorry.
Can I ask you a question on this?
Yeah.
So how flexible is this ansatz in terms of the geometry? Because like you build effectively in the geodesic essentially already, I mean.
Yeah.
So it's already, kind of built in that it gives the right formula?
Yes. So that's a very good question. So with a fixed bound dimension, it's not very flexible. It's almost there's no ability to change the geometry anymore once you put everything on a background geometry. So this is basically the work that has been studied like 3 or 4 years ago. So our new work is going to make this bound dimension even fluctuating. So that will provide us ability to tune the geometry. If the bound dimension goes to basically 1, then that means this bound is effectively disconnected because the bound strength is log of the bound dimension. So that means the geometry is disconnected. And if the bound dimension is very strong, then very large, then that means there's a lot of connection there. So one can tune bound dimension. But for now, let me first talk about this classical, so-called classical random tensor network. Classical means the bulk geometry is classical, meaning that you can't really fluctuate the geometry. So you have a fixed bound dimension, but the tensors are random. But that already, based on that kind of model, one can already evaluate, for example, the second Renyi entropy of the random tensor network state. The idea is that since we say that all these tensor networks, they represent quantum states. So there's a quantum state that you can take from the random tensor network ensemble. And for every quantum state in the ensemble, one can evaluate the so-called second Renyi entropy, which is basically the purity of the state in a certain region. And then that purity basically is e to the minus entanglement entropy. So one can try to evaluate this. And then this turns out, if we average over random tensors, it turns out that this quantity can be expressed as a statistical mechanical model, which is summing over all these internal spins. So it basically becomes an Ising model, where this every random tensor, at every random tensor position, there is an Ising spin. And then this Ising spin is denoted as sigma. And then the model is also subject to a boundary condition, which is set by another Ising variable, tau. And then the model basically is that every Ising spin coupled to each other, if they are connected in the tensor network, and the coupling Jij is related to the bound dimension across this link in the tensor network. And then there is also a boundary condition which try to pin the boundary spin. And the boundary spin is pinned to those directions such that if this boundary belongs to region A, then it is pinned to -1. If it belongs to region A bar, the remaining region is pinned to +1. So basically, that's the Ising model that described. It turns out this second Renyi entropy problem of a random tensor network maps to this Ising model, such that one can evaluate the entropy e to the minus entropy as if it is a free energy, as if it is a free energy condition on the boundary condition, basically. And then this entanglement entropy becomes Ising free energy, and Ising coupling has to do with the log bound dimension. So if the bound dimension is very large, that means the spins are coupling very strong with each other. So in the large bound dimension limits, basically the Ising model will be in a deep ferromagnetic phase. The ferromagnetic phase means that the spins always want to align with each other. So that's why when we introduce this boundary condition, one can see the boundary condition basically creates an Ising domain wall between region A and region A bar because of the setting of the boundary condition. And if the system is in a ferromagnetic phase, then all these boundary spins wants to pin, let's say, a downspin region. And all these upspins wants to pin an upspin region, such that there's an Ising domain wall going across the bulk. And then the free energy always want to minimize the domain wall length. Basically, it's dominated by the shortest domain wall. But the shortest domain wall is nothing but the geodesic through the bulk as well. So that's basically that basically provides a very nice statistical mechanical model that explains why the entanglement entropy of a random tensor network satisfy the Rita-Kanaki formula in the sense that it maps to a free energy, and the free energy is dominated by the geodesic, which is actually the statement of Rita-Kanaki formula. So that is what we can do with classical random tensor network. With a fixed bound dimension, one can basically come up with a static geometry in the bulk, and then this will just provide us vanishing mutual information between distant regions. So that doesn't solve our problem, but that sets the foundation for our study. So our study is based on this, built upon this foundation, and we try to further consider fluctuating random tensor network, meaning that we not only have random tensors where the tensor elements are fluctuating in a Gaussian manner, basically, we also have fluctuating bound dimensions, that these tensor dimensions can also fluctuate. And then this will provide us fluctuating geometry, which hopefully can describe some gravity modes, fluctuating modes. And we hope that this fluctuating random tensor network can better capture things like mutual information, those multi-region entanglement features. And then, and of course, when you introduce this fluctuation, that means either you can say bound dimension is fluctuating, or you can say the Ising coupling is fluctuating. They are equivalent, basically. But if you want Ising coupling to fluctuate, that means your energy function now is not only a function of these Ising spins, but it is also a function of the Ising coupling. And then this Ising coupling will have some probability distribution, joint distribution. These Ising coupling are not independently fluctuating because this gravitational or geometry fluctuation can be collective. So there can be a very, very sophisticated joint distribution of all these couplings, which is unknown to us at present. So we don't know what should be the joint distribution of this Ising coupling, and that is what we want to learn using basically statistical learning, using generative modeling. So that's the idea. So the idea is build a model such that it can match the entanglement data coming from this side, and then we try to learn what should be the Ising coupling fluctuation. And then in order to proceed, there's actually a very interesting idea for planar graph Ising model, that there is a duality for planar graph Ising models, that if you define an Ising model on a graph like this, and then and set a boundary condition such that you create a domain wall in the system, it turns out this kind of a ferromagnetic Ising model can be due to a paramagnetic Ising model on a dual lattice, such that this lattice are basically the face of the original lattice becomes the vertex of the new lattice and vice versa. Such that in the original Ising model, we say that e to the minus entropy is interpreted as basically as a partition function or as a free energy. Entropy is related to this free energy of the domain wall. But in the dual Ising model, it basically corresponds to the correlation function between the dual Ising variables. So, so this domain wall free energy is actually this partition function is actually the correlation function. It's due to the correlation function of this precisely this dual Ising variable inserted at the entanglement cut. So the entanglement cut is basically the boundary of the entanglement region. So remember that we want to calculate entanglement of region A with respect to region A bar. So the boundary is at the between A and A bar. So we insert those dual Ising variable there. The reason that we can do this is because, of course, we can, derive it exactly, but the intuition is that if you really insert two Ising variables here and calculate their correlation in a paramagnetic phase, and we know that in the paramagnetic phase, the Ising correlation in an Ising model will decay exponentially. And then that means if we interpret this as the e to the minus s as this purity, then that means the entropy will be proportional to the distance between these two places through the bulk, because the model is defined in the bulk. And then the distance between these 2 points through the bulk is basically the geodesic in the limits that it's dominated by the shortest distance contribution of this short range correlation. So again, it reproduced the RT formula, but it is just another way of parameterizing the Ising model. But this actually provides us some another way of thinking about this problem, and that is to say, if you want to consider a single region entanglement, for example, you only consider the entanglement of this region A that correspond to inserting two dual Ising variables, and then that correlation will be proportional to e to the minus geodesic distance between them. And then if we want to consider multi-regions, suppose we have A and B, then we need to insert four Ising variables on this entanglement cut. And then that will be dominated by this kind of a correlation between these two and these two, if A and B are far separated from each other. So this kind of behavior is almost like a weak decomposition for free theories that it factorizes. And because of this factorization, here I haven't introduced gravitational fluctuations, so it factorizes as a free boson model, as a massive free boson model. It will factorize. So that basically leads, this factorization means the entropy will be additive. Then that means there's no neutral information. However, with this fluctuating bound dimension in the random tensor network, that means in the Ising model or the dual Ising model, the Ising coupling is fluctuating. That means in the gravity sense, the geodesic is fluctuating. That means not only we want to consider this dominate contribution of the correlation 4 point, when we calculate this 4-point correlation, it is no longer dominated by the classical configuration, but there is actually a fluctuation of the geodesic. And then the fluctuation of the geodesic can be such that it can fluctuate collectively due to the underlying fluctuation of the background geometry. The geodesic fluctuation can be collective. So this collective geodesic fluctuation will contribute additional terms to this correlation function, such that the correlation function is no longer factorizable, and that additional term leads to mutual information. Jim has a question, yes? You want to ask?
Hey, loving the talk so far. I just want to make sure I understand. So this non-trivial joint distribution on the Ising coupling is what's going to encode
yes.
What's going to encode the statistical gravity fluctuations?
Yes.
So,
yes.
so in the limit that that distribution becomes independent, you're recovering zero mutual information. Is that right?
Yeah. If you turn off that fluctuation, say all the Ising coupling is frozen, then you will fall back to the original behavior. Yeah, classical behavior.
So it's really, okay. So it's the breaking of the independence of the distribution that's governing the gravity.
Yes, because the underlying Ising coupling has a joint correlated distribution.
Exactly.
That leads to this mutual information. So that's what
Are you going to do perturbation theory? Or are you going to be close to independent?
In our paper, we have appendix about how doing perturbation theory. You can calculate how this mutual information scales with, for example, the distance between region A and B. And one can show that it can reproduce this power law decay behavior of this. Yeah, that can be shown. Yes.
I see. As a function of some parameter that controls the breaking of
as a function, and the power is controlled by the mass of the gravitation. The graviton also has a mass in this statistical gravity model, and then that mass is basically the scaling dimension that controls this power. And then, indeed, we have some understanding. But for today's talk, I'm going to only talk about machine learning. So basically, that's the thanks for the question. So that's the idea, that mutual information can be mediated by gravitational fluctuations. So conversely, it is in principle possible to extract the underlying, what kind of gravitational model is underlying, can be extracted from this mutual, from multi-region entanglement data. So finally, yeah, let me make a comment that is, so we have been going through all these explanations, trying to describe how we start from the random tensor network and go to Ising model, dual Ising model, and eventually we basically end up with a bosonic model. So the paramagnetic Ising model can be as well equivalently described by a scalar field propagating in the holographic bulk. And then the entropy, according to our understanding of the dual Ising model, is just the correlation function of the scalar field. If you think of this dual Ising variable as a scalar field, because they basically control by the same fixed point in the Gaussian, basically like a massive scalar field kind of limit, if we consider paramagnetic Ising model. So there is a bulk model for the scalar field, that the scalar field, first of all, is massive and it is propagating on certain bulk geometry. But the key point is the geometry itself is fluctuating such that there is a probability distribution for this metric tensor. And for the two-dimensional bulk, we consider basically only the space. There's no time here. And then Gij has 3 components, but 2 of the components fixed by the gauge. We know that so there's only 1 remaining parameter that parameterizes the metric tensor, which is basically the Weil field configuration. So such that the metric can be considered as a background metric. But it is locally scaled by the Weil field. So basically, we can rewrite everything as a massive boson propagating in the bulk, and the bulk has certain background geometry, but we also allow Weil field fluctuation. So that's kind of like a perturbation around the background. And using rigid calculus, we can basically discretize this massive boson model on a lattice. And you should really think this lattice is just the dual lattice of the dual Ising model, basically. And then the scalar field, the boson field, the matter field, basically, the scalar field basically correspond to the dual Ising variables. And then the Weil field basically will describe how this whole background will fluctuate. And then that's the idea. So for every given Weil field configuration that is basically given the background geometry, then there will be, one can calculate the boson correlation, any point, multi-point boson correlation, because this is basically a Gaussian model for boson. So that can be calculated efficiently. And then we also want to sum over all kinds of Weil field configuration weighted by the probability distribution of the Weil field. And once we perform that kind of average, and that average will provide us a prediction of the entanglement entropy, actually e to the minus entropy. And then that will be matched with the data such that in order to extract the Weil field probability distribution, basically. So the point is how to model this very seemingly very complicated joint distribution of this Weil field configuration. The idea is to use a generative modeling from machine learning. And the model we use is a flow-based generative model. It has a few advantages. It has tractable likelihood, efficient sampling, and latent inference power. So the idea of a flow-based generative model is basically to model a probability distribution. But in order to model a very complicated distribution, we can start from simple distribution. Idea is to use a trainable bijective map to deform a simple prior distribution to the target distribution, which is complicated, to the target distribution you want to learn. For example, we want to model certain Weil field distribution. We can start from certain latent variable Z, which follow very simple, let's say, Gaussian distribution, and then independent Gaussian distribution. And then we use a generative map, which maps this this latent variable to the Weil field configuration on every point of our lattice. And then, this under this map, the original prior distribution will be deformed by the Jacobian of this map, actually inverse Jacobian of this map, and then to the target distribution. So now this map itself can contain neural network parameters because this bijective map can be modeled by neural network made of bijective units. And in each unit, there are parameters to tune. So by tuning this parameter, we're tuning this map. So if we tune this map nicely, so one day, suppose after the algorithm converge, we will be able to model an unknown distribution just by tuning this bijective map. So that's the idea. And then one can also, it also provides us some flexibility of designing symmetry. For example, we know if the system has translation symmetry on the boundary, then the bulk should also have this kind of translation symmetry. I mean, translation meaning that means this rotation symmetry. Basically, if you use this picture, then one can basically share parameters or do something like that. And there are ways to basically make this bijective map symmetric with respect to the symmetry that we want. So in this way we can, yeah.
There's a question in the chat.
Yeah. Okay. I didn't see the chat. What is the field AX? Oh, okay, sorry. Yeah, I didn't talk about the detail. So, so this rigid calculus basically is a discretization of this gravity of this model. But this model, when you we know that, for example, square root of G basically correspond to the volume form, right? So when we calculate this summation, we need to take care about the volume. So this A basically is the area. Area is the volume in the 2D case. So this A is AX is the area around vertex X. X is the coordinates that labels the vertex. So there are some details there. But this AX, of course, is also related to the geodesic length of each side. So that's just a discretization of the rigid calculus. But I should say that all these background geometry, the background geometry is fixed. So this we kind of put it already on we assume that the background geometry has a hyperbolic geometry, but there are still a lot of parameters. For example, how do you parameterize the coordinates, and then what is the mass? For example, there are still a lot of a few parameters in this model that is also subject to learning. That's also part of our model parameters. But most of the model parameter coming from this generative model. Yes. Okay. Jim, you have a question? Yeah.
Just a quick question. XY.
XY is because, XY is because this is like an on-site summation. Then you basically need to take care of the area around a site. And then this is basically the link summation. You need to take care of the area surrounding a link. So this AXY basically is the average of this A. For example, the AXY associated with this link, this is X, this is Y. And then it's basically the average of these two areas in some sense. Yeah.
So AXY is 1 or 0. What is the value AXY?
Oh, AXY is it's not a binary variable. It's just some real number, which is actually the area surrounding the link XY, basically. So
surrounding a link. Okay, thank you. I understand. Thank you.
Yeah. You need to partition the full area into separate areas surrounding each link, such that because this integration involves this area element or volume element, so you need to do that kind of partition. There's a little bit arbitrariness, but in the limits that your discretization is fine enough, it should approximate the original continuous model. Yeah.
Thank you.
Further questions?
Just to make sure I'm understanding real quick. So you're choosing to use a flow because to do the matching that you want to do, you need a tractable density. Is that right? Yeah.
That's one way. And I think another thing, actually, in order to learn this generative model, we only use its generative power. In the training, we only use sampling. But the nice thing is that after training, you can use this tractable likelihood to evaluate the action of any wire field configuration. Yeah. So you give me a new
see.
configuration. I can tell you what's the action associated with this configuration by taking the negative log likelihood. And
Yeah, so,
the likelihood is computable in this way. So you automatically get the action, not only.
I see. So why did you choose? I appreciate the point that you just need the sampling from the point of view of the actual training procedure. Why did you choose a flow-based model then?
Yeah, you can use other model as well. I think
okay.
You can also
okay, so
use.
It's not that it was critical.
Yeah. It's not a must. I think. Yeah. It's just happen. It happens that we use that. Yeah.
Okay, I see. Thanks.
Okay, so eventually, this is the architecture. This is the general algorithm. The idea is that we start with a generative model. The generative model will start from a prior distribution, and from this prior distribution, it will sample latent variables. And the model will also have a few model parameters, such that there is a generator, which is a bijective map, which maps all these latent variables to the wild field configuration, to a set of them. So this process is basically sampling from the generative model, a collection of wild field configuration. For each wild field configuration, there's a bulk model solver. So the bulk model solver is solving this kind of model and calculates, based on this energy function, calculate this basically multi-point correlation. So the bulk model solver will solve this correlation function given the underlying wild field configuration for each of the sample that we sample from the generative model. And then, of course, you need to also tell the model what kind of correlation you want to calculate, where you should insert those dual Ising variables or the scalar field. So this region A information is also told to the bulk model. So once the correlation function is calculated, and then we take the average of this wild field configuration, negative log average, will give us a model estimated entanglement entropy, which depends on the model parameter. So on the other hand, if you have a region A, one can also go to the data set. So the entanglement data set is something that we prepare separately, which contains the actual entanglement entropy of every region A. So for every query A, we basically calculate the model prediction and compare with the data by the loss function. The loss function goes to 0 if the model matches the data. So by minimizing this loss function, we can gradient backpropagate the gradient all the way to the model parameter. In this way, we can train our generative model. And then the entanglement data is collected from 1+1 dimensional massless Majorana fermions, which is a 1+1 dimensional CFT, which you can solve it on the lattice and very efficiently. And yeah, so that's the general setup. So the entanglement data we collected from some free fermion chain with 32 sites with a rather large central charge. We use multiple of the Majorana fermion chain such that the central charge is large. The reason that we use a larger central charge is we hope that we are not too far away from the classical gravity limit, such that we only model this perturbative fluctuation on top of background geometry. So we can have different models. Indeed, we can turn off our fluctuation, although we have a generative model for the background geometry, but we can choose not to use that. We can basically turn off the generative model and use a static background. The model still learn. The model still has some fitting power. And then we can also train this model by using single and two region entanglement. And we can test the model by asking it to predict 3 region entanglement, for example. So this is what we have been testing. So if we start with a static model and train with a single region entanglement data, it turns out that the model has a very nice prediction of single region entanglement data, but it has a not so well prediction for double and triple region entanglement. So these numbers basically is the final loss function, or basically the relative error in e to the minus entropy. So that is basically the prediction error. So if you train on single region data, of course, it predicts single region well, but it fails to predict double and multi-region, triple regions. But if you train with single and double region data, it predicts both of them okay, but it loses the predictivity of a single region. It loses that kind of a nice 10 to the minus 6 arrow there. So, so that means there's some internal inconsistency between single and double region entanglement. That is precisely the mutual information kind of data. That kind of data cannot be captured by the static model. So the static model try very hard to fit all the entanglement data, but still cannot do a very good job. But with the fluctuation, we can see there's a significant improvement of the relative error in both single and double region data. And even it has a better prediction for triple region data, even if it's not trained. So it provides a better model for multi-region entanglement. So if we can really look at pictures. So this is the picture of a predicted single region entanglement. So this is the region size. So we are talking about single region. So this is the entanglement entropy. The black line is the ground truth. And the red dots is basically the model prediction. And this model prediction, this picture is the model that we use a static model and train on a single region data. So you can see the prediction is very well. And the point is that if you only look at the single region entanglement, you don't really need any gravitational fluctuation. Already a classical geometry can very nicely predict, can fit every feature of a single region entanglement. So if you only consider single region entanglement, there's no need of a fluctuating geometry. And then this is basically, this picture is the same thing, but we basically use, we basically compare a static model, but we train it, if we train it with both single and double region entanglement, you can see it sacrifices a little bit single region entanglement kind of prediction. But if you include the fluctuation, then it can pretty much still capture the single region entanglement. So that's, so I should say this is not the main point. The main point is mutual information, right? So the mutual information you can immediately see the difference. So if you use a static model, if we use a static model, this is the mutual information between region A and B. These different pictures is different pictures that region A and B are of different size. And then the horizontal axis is the separation of A and B. So the distance between this region. So, so this black line is the ground truth. So the blue dot is the fluctuating model. If we include the gravitational fluctuation, we can capture the mutual information much better than a static model. The static model is also trained on both single and double region. So in principle, if it can fit everything, it should be able to learn this mutual information, but it can't because it doesn't have the ability to fit this mutual information. It's intrinsically not being able to be captured by a static model. So we can see introducing gravitational fluctuation or this geometric fluctuation indeed help to improve the prediction power of the model. So that also means that it learns something, it really learns something about the fluctuation from the mutual information data. Yes, questions?
Yeah, this is awesome. I do have a question. You mentioned that another group added an extra field to the theory to try to account for this. And one advantage of yours is that by just using gravity, it's more minimal. But is there any, there's sort of a phenomenological question of what setup does the best. Do you have a comparison to theirs?
Oh, you mean introducing matter field to mediate?
That's right. You said that another group did that. So there's a phenomenological question of what, you know, what sort of physical addition best accounts for the
yeah, I feel my personal feeling is that my feeling is that if you don't compute anything like a really any field correlation function, if you just consider gravity, if you just consider entanglement property of a quantum system, there's no difference of this entanglement mutual information mediated by a matter field or by a gravitational fluctuation. Because in general relativity, we know that any mass can be replaced by basically gravity, by geometric deformation. So, if you only calculate entanglement, entanglement is basically those kind of gravitational properties of the quantum system. So it doesn't matter whether you use a matter actual matter field or a gravity field. It will matter if you really calculate specific correlation functions. Yeah, that distinguish matter field from gravity field. Yeah.
I see. So this is a sort of a minimal approach that at the level of entanglement.
Yeah. I think this is the minimal approach. Yeah.
But for other correlators, you might need to do more phenomenological engineering.
Yes.
I see.
Yes.
Thank you.
So entanglement basically is the correlation of twist operators. So for that, you don't really need actual matter field. Yeah. So
sorry,
yeah.
Can you go back one slide?
Yes.
One more slide.
One more slide. Okay. This.
So in this case, there is no reason why the static model trained on both is actually going down in accuracy. I mean, this is without mutual information. So in this case, static model should in principle still be able to describe this.
Yeah, because the static model can't consistently describe both single and double region entanglement. So if you train it with both data, then it is very confused. So it actually sacrifices a bit of its single region prediction power in order to try to model double region, but because it can't really do that. Okay. So that's why it sacrifices its performance. Yeah. Okay, so the previous data basically shows that the model really learns something. So we can really open up the model and try to see what kind of correlation it learns. For example, we can define the wild field correlations, which is basically based on the model machine learned probability distribution. We can evaluate the wild field correlation at different points, X and Y. X and Y are points in the bulk. And then this is the covariance, I believe. And you can also define correlation, which basically normalize the covariance. And then this picture is a plot of the correlation function. So this is the correlation from any other point with respect to the white point. So the wild field at a reference point, and then you can see what's the correlation with any other point. And the color indicates correlation. Color goes from 0 to 1, let's say. So one can see very nicely there is an emergent locality. That means the wild field indeed, although when we set up the generative model, we didn't impose this locality on the model level, but after learning, the model learns that there is a certain kind of locality in the wild field correlation, that the correlation actually decays in the bulk. And then if we study more carefully, we can actually verify that the wild field correlation decays exponentially in the bulk as well with a certain, let's say, inverse correlation length. And then we can also fit the inverse correlation length at different layers. And it's almost, that means different layer means, for example, this is first layer, second layer, third layer. So it is almost universal in the bulk. And then that means there's almost like a uniform bulk local model description for the wild field. So we can even start with this covariant that we obtained from the learning, and we can calculate the covariant matrix and do a spectral decomposition and find the leading eigenvalues and also the leading eigenmodes. So and then we can plot these leading eigenmodes, and then they tells us how the wild fields are fluctuating. So with certain eigenvalue, the wild field can fluctuate either collectively, meaning the whole space is shrinking and expanding, or it can fluctuate with a P wave, D wave, and higher order, like these modes, meaning that when this part is expanding, this part needs to be shrinking. So there's correlation. Yeah.
So two things. First of all, do you think you can wrap up in 5 minutes? I know we interrupted.
Yes. Okay. Yeah, just 5 minutes. Towards
the end. It was a raised hand.
Yeah.
Yeah, so I have a question on regarding locality, because like in what sense before training, so how unlocal can it actually be?
Yeah, it's before training, the bijective map is designed to be all-to-all, basically. So it is starting from some random Z. And then it maps to. I mean,
the reason I ask is because like that depends right on your architecture that you choose, like what kind of.
Yeah. Then we we deliberately choose an architecture that is all-to-all, that is fully connected, that has no locality, because we don't want to impose that by hand. We want to test the model indeed learns locality. We want to see locality as an emergent phenomenon, not something that we impose. Yeah. So when we design this bijective map, G, generative map, it is not designed with locality. Okay. It is not using CNNs and things like that. It's non-local. Yeah. It's actually using a CNN with a large kernel. The kernel size is half of the system size. So it's like, the CNN is used only to impose translation symmetry, to share parameters, but not to impose locality. Yeah, that's the idea.
Yeah, thanks.
Okay, so any question?
Sorry, for one region, the picture before this picture, for one region, before this, yes. Before this, oh yes. You have two pictures for one region. What is the difference between?
The difference is the ground truth is exactly the same thing. The difference is using different model and using different way of training. So this is the model. Static model means doesn't include the gravitational fluctuation. And this bracket, in the bracket is the data that used to train the model. You train it with a single region data or train it with both single and double region data. And the performance can be different. This picture is just trying to say that if you use a static model trained with both data, its performance not as good as a fluctuating model, meaning that fluctuation is important basically in order to capture the feature of the data.
Both states, what both?
Both means trained with both single region and double region data, entanglement data. Yeah. But you, after training, you use it to predict single region entanglement. Trained with both data and used to predict single region entanglement. Yeah.
Thank you.
Okay. Yeah. Okay. I think that's towards the end. So in the end, I want to say that, of course, with all these studies, one can also study, for example, the wild field fluctuation. We can study its covariance and do spectral decomposition, understand what is the dominant gravitational modes, and one can even write down Gaussian model. For example, if you want to just satisfy with the Gaussian level description, this will be the action for the gravitational theory. So that means we really can extract a sensible theory from learning. So the conclusion is that this learning try to fit the multi-region entanglement, and the model after learning will learn the underlying statistical gravity model. And then of course, in this case, it's in terms of the wild field fluctuation. So this provides a data-driven approach to establish the holographic duality. I will maybe skip this, and then the summary is basically, we basically provide a machine learning approach to extract holographic statistical gravity theory from multi-region entanglement data. In this work, we generalize the random tensor network holography to include the bound dimension fluctuation, and turns out that's very important in capturing multi-region entanglement. And then this will give us a data-driven approach to discover the gravity fluctuation from entanglement. And it turns out there's an emergent locality, which in the gravity model, which I think is very interesting. And then for practical use, this actually also provides a predictive model for quantum many-body entanglement structure, meaning that you can train the model with with partial entanglement data and use it to predict entanglement of these quantum states in other regions that you can't really measure or you didn't measure. So this kind of functionality will be useful for quantum circuit optimization and quantum algorithm design in quantum information, basically, because there we need to know the quantum, the entanglement feature of a quantum circuit there. So, I think more profoundly, in the future, I mean, the big thing is basically, can we use data-driven way to discover new physics from data, physics theory? So you can see, not only we are trying to fit the data, we really try to learn certain gravitational actions that come behind those entanglement data. So with that, thanks for your attention. Yeah.
All right. Thank you very much, Yi-Zhuang You, for the wonderful talk.
Thanks.
Thank you for our clap emojis. We're running a little bit late on time, and we already had a lot of questions, but we can.
Sorry.
No. We interrupted you. It's our fault. But yeah, so we have time for a few more questions. But of course, if you have to leave, please feel free to leave. Yes, Sven.
Hey, yeah, so just a technical question on system sizes.
Yeah.
So how large a system size can you push it? And what are the limiting factors in terms of?
Oh, okay. Yeah. We do all this on our personal computer. We didn't have resources. I mean, the goal is not to push to very large system size. So I don't know how, we haven't tested that. So I think this training is just done in, as I recall, this training is done in within 10-20 minutes like that on a personal computer. It's not trying to push any limit. Yeah. So the current system size we use is a fermion chain with 32 sites. Yeah.
Thanks.
Okay. Yeah.
Tim?
Hey, Yi-Zhuang, that was an awesome talk. Just one more question out of me. So to get a local theory of statistical gravity, you could also check the higher correlators in the Weyl fields. Did you guys compute those and or check them for locality?
Yeah, that's a good question. Yeah, we haven't. That's a good suggestion. Maybe we should. Yeah. For example, we can calculate 4-point to see whether it's a free theory, right? Yeah.
Exactly. So the higher correlators, because you have the learned distribution, in principle, if you were powerful enough, you could compute any higher point correlation function and then check for cluster decomposition or something like that.
Yeah, all those can be checked in principle. Yeah.
Wonderful. Well, beautiful talk. Thank you.
Yeah. Yeah.
Sorry, and what is free fermion with large central charge? Free fermion, what is it?
This is the Hamiltonian for the free fermion model. This is the Majorana operator, and then it is defined on a 1+1 dimension, basically one-dimensional lattice.
Yes.
And then this model has a fermion has a dispersion, like a linear dispersion near the Fermi surface, and then it has a entanglement, which is basically this is a CFT, and then.
No, but in this Hamiltonian there was no C.
The C is n divided by 2. This n is a flavor. So fermion not only has a site index, it also has a flavor index. And this flavor index goes from 1 to n. That means we have n copies of the Majorana chain. And then this n divided by 2, every Majorana chain contribute 1/2 of the central charge. Yeah. So yeah. We just want to approach the classical limit in this sense. Yeah.
Can you go again to the plot where you were showing the correlations in non-locality?
Oh, yeah.
Yeah, this one. Oh, yeah, the one before.
No, the before, yeah.
So here it seems that sort of they reach roughly the same. I mean, the non-locality or the C is located around the lattice point, and then it reaches approximately the same way, but the geometry of the, I mean, the closer you get to the bulk, sort of the, how should I say?
When you get to the bulk, it's more spread because the bulk metric is different.
Yeah, exactly. But here it seems to be all the same size. So maybe it's an artifact of plotting this, but
yeah. You shouldn't read this exactly as if you think that there should be an ADS geometry, because even how to parameterize the coordinate is learned. We didn't use the standard. We didn't equally space this radius direction. We just let the machine to learn the way to best parameterize because it also matters how you discretize, right? This is also something you can let the machine learn by itself. So the coordinate is not evenly spaced. But when I draw this, as if they are evenly spaced, but you shouldn't think that way. Yeah.
Okay, good.
We actually, in our paper, we explain how eventually machine learns the coordinate, how it distributes along the radius direction. It's not evenly spaced. We check that. Yeah. Yeah, machine thinks it's a better way to not to evenly space the coordinate. Yeah.
Okay, I don't see any further questions. So let's all thank Yi-Zhuang again for the very nice talk.
Thanks, everyone. Yeah.